Hello, Internet. We are live.
Everyone, welcome to episode 23 of the Stanford MLSys Seminar series. I'm Karan. We have with us today Fyodor, Piero, Dan, and our guest today, Erin LeDell from H2O AI. This week, we're going to be talking to Erin about scaling and automating machine learning at H2O AI. So as always, the plan is going to be a 30-minute talk followed by a 30-minute podcast where you can ask questions in the live chat, and we'll keep track of those questions if you want to keep them coming during the talk as well. A bit about Erin. She's the chief machine learning scientist at H2O AI. So she focuses on automating machine learning, ensembling, and statistical computing more generally. Before this, she was principal data scientist at WiseIO, and even before that, she got her PhD in biostatistics at Berkeley. So really a long and interesting career, and we're really happy to have you, Erin, talking today about scaling machine learning with H2O and also algorithm development at H2O. Take it away.
Okay, thanks for having me. So yeah, usually when I talk about H2O, I'm more in a teaching role, teaching people how to use the software, etc. So it's been a while since I've had a chance to talk about the system itself. So I appreciate the opportunity. So yeah, I'll just start with kind of an overview. I'm just gonna probably spend the first maybe 15 or 20 minutes of the half hour to just talk about H2O and the distributed machine learning platform. And then I'll talk a little bit about H2O AutoML. That's where I focus a lot of my time now, which is an automated algorithm on top of all the H2O algorithms. And then just because this is kind of a systems focused seminar, I thought it might be kind of, I don't know, useful or interesting to talk a little bit about how I use systems as part of my development process for designing an automated machine learning algorithm. So I'll touch a little bit about how I do that and what the tools that I use for that are at the end. So first of all, so H2O is a machine learning platform. So I use the word platform instead of library because it's sort of self-contained. It has sort of all the infrastructure that you need to do the machine learning as part of the platform itself. So it's distributed. So that means, in our case, it means multi-core and multi-node. So all the algorithms are basically written from scratch in Java in a way that can scale to basically as many nodes as you need. And of course, there's communication overhead the more nodes that you add. So ideally, you choose hardware where you can minimize the number of nodes that you need to use. But H2O has been around since 2012. So if you think back to what was going on at the time in 2012, so that was AWS was getting to be quite popular in EC2, and cheap compute was sort of everywhere. It was like kind of right on the cusp of when, like right before people started using GPUs for everything. And when compute became very cheap. So kind of one of the goals of H2O was to take advantage of that compute situation, which was cheap CPUs at scale. And also around that time, like I think basically the only other sort of known or sort of popular machine learning platform at the time was something called Mahout, which was written on top of Hadoop. And it was pretty basic, and it didn't really have that long of a life. I don't hear people using it nowadays, but there weren't really a lot of systems that were at least widely used for doing machine learning. A lot of people were using scikit-learn. A lot of people still use scikit-learn. And that's probably like the closest thing that you can think of when you think of H2O. It's just a library of a bunch of different algorithms with a common interface that's sort of self-contained. So yeah, I already mentioned that the algorithms are written in Java, but really like machine learning systems, if you want them to be kind of widely used by data scientists, you need to have at least a Python API, and we also have an R API as well. So so yeah, you can use it as in Python, in R, in Scala, and we also have a web, like a full-on web GUI. You can't do a lot of like the data munging stuff in the web GUI, but you can train algorithms and basically do anything that you need to do without writing code. And then one of the other issues that we were sort of trying to solve with H2O was that it used to be, this probably still is kind of a design process nowadays, but at least back in like the early 2010s, what would happen is you have like a data scientist sort of prototyping something in R or Python. And then if you want to take that to production, you probably have another engineer coming in and sort of rewriting everything in C++ or Java or whatever it was at the time. So we were trying to basically close that loop or close that gap. So you can be sort of a statistician or a data scientist who's not really like a systems or engineering type person and do everything, in R or Python. And then what you can get out of that at the end is these easily deployable models that are able to be deployed as just pure Java code. So we have a couple different ways to deploy models, but that's kind of, one of the main goals was like, how can we build really, really fast, like production level models where you're, let's say you need like, sub-millisecond like prediction times, things like that, where you're either needing to make a lot of predictions at once, and so you need them to be fast, or you're just serving predictions in a very fast way that you need the speed. So so originally, like I said, it was built around 2012, so that was sort of the Hadoop era. Spark was just getting started around that time. So it hooks into Hadoop. We actually completely rewrote everything to work with Spark. So when you go to our repo on GitHub now, it's called H2O-3. So this is actually the third incarnation, and that was like around, it was like right when I joined the company around like 2015. So it works very seamlessly with all these big data systems, but a lot of people just use it on their laptop or on a server. You don't actually need Hadoop or Spark. It's just sort of there if you are sort of locked into that ecosystem. So that's kind of a high level overview. And then in terms of just what it offers, we've got a bunch of different supervised and unsupervised machine learning algorithms. We try to do kind of everything automatically that is typically required in a data science pipeline. So that could involve like imputing missing data, encoding any kind of categorical variables in any particular way as needed by each algorithm. We have some built-in tools for early stopping, so you're not overfitting. And then we have everything else that kind of goes with machine learning: cross-validation, grid search, random search. Then once your models are trained, we've got variable importance for everything, model performance metrics, et cetera. And now we've got model explainability. So that's just kind of generally what H2O is about. Okay, so let's talk a little bit about the distributed computing aspects. So kind of two of the main things that you need to know if you're going to work with H2O is one, something that we call the H2O cluster, and then two is what we call the H2O frame. So the cluster is basically just the name of the shared memory that we use, the Java memory, and it could be running on your laptop, or it could be across a number of nodes on EC2. And there's no limit on cluster size, but as I mentioned earlier, there is communication between the nodes. The data kind of stays where it lives on each node, and then the algorithms sort of communicate, well, the code that's training the algorithms communicate between the nodes to give updates and things like that. So that's kind of how it works. But that's what we mean when we say the H2O cluster. So that's just really a terminology thing. So then we've got the H2O frames. So what this is it's a distributed data frame, and it's the data is a collection of vectors. It's organized by column. So essentially one column of data is spread across a number of different nodes. Let's say you have in this little figure here, we've got four nodes, and some of the rows will be on each on each node. So a whole row will live on one node, sorry. And then the way that these work in practice is that you have this, what we call the H2O frame. And if you're using the Python API, you're just more or less using the same data manipulation API as Pandas data frame. So if you know how to do something on a Pandas data frame, typically it translates into an H2O frame. We basically support a subset of Pandas data frame operations, and the same with R. So if you know how to sort of interact with R data frames, you know how to like merge or split columns or all of that stuff, we're not trying to make you learn a whole nother API on top of it. So we sort of overloaded the existing API to make it easy. Okay, so that's just some terminology. So just a couple more things here. So we have really fast ability to read in data. Oh, one thing I don't know if I mentioned yet. So just because there's a lot of probably deep learning talks in this series. So H2O is for tabular data. So just in case that wasn't clear yet. So we're exclusively working with tabular data here. And so everything that I'm talking about has to do with tabular data. I just thought I would mention that because we're kind of in a space where there's different data types, text, images, etc. So we're exclusively focused on tabular data. And what can I say? So basically, we read in the data in parallel. It gets distributed across the cluster. It's compressed. So when you need a data, like some data, it gets sort of uncompressed on the fly. And so and we do that in a very fast way. The training data kind of stays on its own node. And I mentioned this before, but the data's more or less static, and the algorithm talks in between the nodes to understand how to do that. And then one question sometimes we get is like, why did you build your whole distributed computing framework? There's Spark. And just in a comment on timing. So H2O was built right before Spark. So perhaps if it was like a couple years later and Spark RDDs were quite popular already, maybe we would have built it on top of Spark, but it's very similar to a Spark RDD. And a couple of things about the cluster. So basically in the cluster, everything has a key associated with it. That would be like a model has a key, a data frame has a key, etc. So inside H2O, we have a distributed key value store, and that kind of references where everything is, because again, we have multiple nodes, so things live in different places, and we need to know where things are. Each key is actually like associated, has kind of a home node, but the key value system itself is peer-to-peer, and there's no like centralized name node. And just a couple other things, if you care about things like this. So, it's very fast, essentially, is what I'm trying to say here. So a typical get or put takes 150 nanoseconds. So it's very efficient. And yeah, it's fast to move data around or to reference data. And then a couple other things just about like how it works. So we have a reliable RPC mechanism, which can retry failed communication. So let's say, we were building this to be robust on top of EC2. So let's say that, possibly your nodes live in different places. They might not be all at the same data center. So what happens if it's training an algorithm and some data gets dropped between the nodes? Well, we just have something built in to basically handle that. So you can unplug nodes and plug them back in, and it will eventually just recover whatever it was trying to do. And then just some technical notes. So the algorithms are implemented on top of H2O's distributed MapReduce framework, which utilizes the Java fork join framework for multi-threading. So just some more technical details. And a couple comments about, I won't go into detail about all the different algorithms and all the tricks that we do to figure out how to get this to train fast in in a distributed setting, but like basically each algorithm is sort of, we take a new approach, and whatever's required for that particular algorithm, we figure out a way to make it distributed. So something about the tree-based algorithm. So each tree is actually fully, so when we train a tree, we train one tree at a single time, and it's parallelized across the whole cluster. So H2O also, if you think back to 2012-ish time, you know, everyone was talking about big data, and so big data was like a very important thing, and still is a big thing. But one of the design choices that we made was it's optimized for training really, really large data sets. It's not, so you kind of have to make some choices when you design a system. So one, we could optimize it to train, like, let's say hundreds of models at a single time. That would be one choice. But we did kind of the reverse of that, which is to train like a single model in a fully parallelized manner so that we could really, really work on big data. And so that's, you know, I don't know if other systems are designed differently to kind of do lots of training at once, but this is kind of the approach that we took, and therefore it scales to, you know, extremely large data sets, like terabytes of data, you know, hundreds of billions of rows, that type of thing. So so that was, you know, some of the things you'll notice is, like, if you do try to run it on like a really small data set, you might be able to use a different machine learning algorithm and get a better result if that was optimized for small data. But once you know, have, say, 50,000 rows, you'll start to really notice that H2O is quite fast. Let's see, so yeah, a lot of people like the tree algorithms like GBM or random forest. We also wrap the open source XGBoost. So we were, you know, there was a lot of demand for XGBoost. And so one of the things that we did was, and this is actually the only algorithm that we've bundled in with H2O, but basically we wrap the open source XGBoost. And I should also mention that up until now, like everything that I've been talking about is all CPU. And XGBoost is the only algorithm in H2O that has GPU support, and that's just because it comes in, you know, third party, and it's already there. So if you do train an XGBoost in H2O, it can use the GPU as well. But otherwise, it's exclusively a CPU-based system. So for deep learning, what does that mean? So most deep learning systems are GPU these days, or, you know, at least CPU/GPU. So what we've done is we kind of focused on a particular use case. So like the fully connected, you know, multi-layer deep neural network, and just kind of made an optimized version of that, and really have not tried to kind of replicate like PyTorch or TensorFlow or any of that. There was a point where we made something called Deepwater, which was basically a, let's say, a wrapper to a bunch of those other tools. And it was just, you know, it was just quite difficult to maintain because, you know, we're in Java. Once you're in Java, it's like kind of, you know, you're in your own world a little bit. And so we did have something that was functional for a while, but then made the choice essentially to sort of cede that domain to the people that were already excelling. So I don't know. At that time, it was TensorFlow, it was Caffe, and MXNet was the one that we were supporting. And then Keras came along and things, you know, so we just really try to focus on tabular data and doing well there. So GLM, that's another really, you know, still widely used algorithm in the enterprise environment. Like, so many people are using just GLMs to do all sorts of things. So we have like a very highly optimized GLM that scales really well. We've got a bunch of different solvers. The ADMM algorithm by Stephen Boyd at Stanford, you might be familiar with. That's something that we use. So actually, the three advisors or academic advisors at H2O are all Stanford professors. It's Stephen Boyd, Rob Tibshirani, and Trevor Hasty. So we've been working with them since the beginning, just, you know, consulting and getting ideas, and that's that's essentially why we use ADMM in the GLM. So yeah, so we have a lot of influence from those people. And then there's a bunch of other algorithms as well, but I won't go into detail. All right, so let's talk about AutoML. So the AutoML algorithm is something that that I started working on in probably maybe late 2016, and it came out. The first version was in 2017, in like June or July of 2017, and so this has been kind of a long project for myself. So essentially, what I was finding is that I'm typically writing a big wrapper function of everything that I want to do with H2O when I approach a problem. And then eventually that kind of just morphed into, well, why don't we just make that a function and call it AutoML? And then, then we have this sort of automated, simple algorithm that does kind of like a sensible thing, or like sort of encodes at least my process of what I think is a sensible approach to any arbitrary machine learning problem. And so that's kind of how it's evolved over the past couple of years. And just kind of as a motivating idea, like, why do we do AutoML? And I mean, maybe this should be, or maybe this is kind of obvious to the people watching, but just, just for fun, let's have a quick discussion. Why AutoML? Well, I mean, essentially, you can't really predict which algorithm is going to be appropriate for your data in advance. You might have some guesses based on your experience as a data scientist. If you have a lot of experience with different types of data sets, you might have a certain type of data set. Maybe it's like very, has a lot of high cardinality categoricals in it. So that might make you think, okay, which algorithms would be good for that? Okay, I'm going to rule out this, I'm going to rule out that. So you might have some ideas, but it's really hard to kind of sort of encode that in an algorithm. So, so my personal approach to AutoML is that you really should consider all types of algorithms if you want to really get good coverage. And so this is sort of there's a sort of idea which you've probably heard of called the no free lunch theorem, and essentially it's just there's no single best algorithm is kind of the motivating factor. So some AutoML tools kind of focus on one algorithm, like XGBoost, or if it's just deep learning or something like that. But the approach I've taken is just to kind of try everything. And so so that means that I'll explain what that means in a second. I have a slide on that. Okay, so let me just sort of briefly give an overview. So automated machine learning would include any kind of like data preparation that you might have to do, or feature engineering, or encoding of features, and then models. You have to basically generate a whole bunch of models. At this point, I do think that in the future that there'll be a little bit more machine learning built into AutoML. So maybe you can predict based on a whole bunch of data about what algorithm might be good, and kind of skip over the brute force approach. I do think that's maybe where AutoML is headed, but we're not quite there yet. So essentially what it looks like today in 2021 is that we have to generate a whole bunch of models and evaluate them and see what's going on. And then this last piece is ensembles. That's optional. That's just kind of something I like to do. So the algorithm, what it does is it has some basic data pre-processing, and then we've defined like a random search across a bunch of algorithms. And so kind of the hard part is allocating how much time should go to which algorithm and where to focus your effort. Because if you have kind of infinite time, you can just try everything and eventually get to a good solution. So I will mention this on another slide, but basically the hardest part about AutoML is to kind of prioritize work and decide what's going to pay off. If you only have an hour, or if you only have 2 hours or 30 minutes or 8 hours, whatever the time limit is, like the goal is to get the best model within that time. And that might look very different if you only have a short amount of time versus a long amount of time. So we have some way of sort of allocating time in AutoML, and then we also train some stacked ensembles when we have the algorithms at the end. And kind of what you get back is what we call a leaderboard. This is just briefly what the code looks like. So essentially, AutoML tools are mostly just like one line of code, or in Python, we've got 2 lines of code, but that's what it looks like in R. And that's what, one of the things that you get back is sort of the sorted leaderboard of all the different models that were trained, ranked by performance. And you can rank by other things too, like prediction speed or other things that you might care about. Okay, so I've got 5 minutes. So then let me just briefly kind of walk you through what the development process looks like for me. So, so this is the slide that I mentioned before. So the hard part about AutoML is sort of, it's like an allocation of resources, and how do you decide, like, okay, based on what I know about this data set, should I do like XGBoost first, and how much XGBoost should I do, or should I bring in some deep learning, or should I just, you know, it's this very tricky sort of infinitely configurable space where you just have to make decisions and hope that your decisions make sense and that you're going to get good results. So, so I would say the first couple years of me developing the AutoML system was just, let's get something that makes sense and that works, and then focus on usability and other things. And then I would say the last couple years, it's like, okay, now we have something that works pretty well, but now how do we improve the system? And how do we guarantee that when we make changes to the system that they are actually improvements, you're not just overfitting to some data sets that you typically play around with. So it's really important to be able to measure all the changes that you're trying to make or the experiments that you're trying out. And so AutoML is unique in the sense that there's no reference algorithm. So there's no just like random forest and let's implement the random forest and get it faster than the existing random forest. It's, you know, there's no rules and we can do whatever we want basically. So how do we do that, and how do we know that we're doing well? Because it's such an open problem. So we really have what I call like benchmark driven development. You have to measure everything. So for the past couple of years, I've been developing this other system with a number of other AutoML researchers that we call the AutoML benchmark. And it really didn't come out of a development motivation. It came out of once the, you know, sort of big, let's say, corporate interests, like other big companies in this space started to create AutoML tools, the benchmarks that were getting basically put out were just all like marketing, essentially. So we, you know, there's this word that we use called benchmarketing. And so, you know, somebody has a new AutoML tool and they release some plot where their tool is better than all the other tools. And it's just, you know, it's nonsense basically. So we decided like one thing that would be important as this field evolves is to have a very scientific approach to comparing tools. And so we kind of got together a bunch of researchers and started building a system that we felt would be sort of fair and reliable and reproducible for measuring AutoML systems. And we call that the AutoML benchmark. And we have an ICML paper about it if you're interested. And OpenML, I should just mention, is an existing platform to do machine learning benchmarking. So we built on top of that. It's basically an API that you can query with metadata about data sets, and you can query, you can actually get the data sets as well. So essentially what this is it's a framework, but we've also sort of defined what we believe is a sensible set of data sets that we can benchmark different things like binary or multi-class or regression problems. And it's all, you know, open source. It works with Docker and you can execute it locally, or it's actually quite easy to use on Amazon EC2, and that's typically how I use it. You can add your system to the benchmark. So the first version of this, we had about 4 tools. So AutoSKLearn, Teapot, H2O AutoML, and then we had this a little bit older tool called AutoWeka. And in the past 2 years, like now all the big open source tools are getting added to the benchmark. And so they just make a PR and they add themselves. And so now we can really have a good overview. But okay, it's 1:30. I'll take like 2 more minutes to just finish my slides. But I just want to quickly walk you through like an example of what how I do this. So this is something that I've been doing over the past couple weeks, this particular example. So I was noticing that, I'm running AutoML for a long time, and one of the things that we do is this train a stack ensemble at the end. And typically it's always the best model, but that's not necessarily, you don't want like a 200 model ensemble necessarily to put into production. So one of the things that I was thinking, why there's too many models that are like activated in the stacked ensemble at the end. So, why don't I try just adding some more regularization to the meta learner in the stacked ensemble algorithm, which is a GLM. So basically, I tried out adding a grid search on alpha on the GLM, and instead of just a default. And then I want to experiment on all different types of data sets in this case, because this is like more of a general problem. Some problems are unique to like subsets of data, like small data or big data or data with other issues. And then so I make a branch of H2O, I try it out, I run it on the AutoML benchmark on whatever data sets I choose, and then we measure the effects of that. And then these are just some considerations that you have to think about, like what set of data sets do you choose? Are you trying to look for, if you're looking at fixing class imbalance, you might want to collect some some imbalanced data sets and benchmark on that. The resource limits is another thing you need to think about, like what are you trying to optimize for? And then when you're done, we can like examine the results. We built a little dashboard. It's on GitHub if you want to try it out. It just takes the results from the benchmark experiment and basically plots them. And this is just a new thing that that my intern in the last couple of months had developed. Viviana Hernandez is her name, and so we're going to add a bunch of new visualizations to this, but it essentially looks at all sorts of things, like model performance is one of the main things, but when you're tweaking things, and you still need to think about, like, if you care about production use cases, like how fast are the resulting models? Are they much slower now that you added some complexity? So we have to so one sort of tip that I have is don't focus exclusively on model performance, because you might be kind of missing some other things. Like we've seen that actually with people participating in the benchmark, they focus a little bit too much on model performance, and then they get these models that are like really, really slow to use in production. They're not very practical in real life. So we're also adding more aspects to the things that we measure in the benchmark as well. So I will leave it at that. The rest of this is just resources. If you want to read about the H2O AutoML algorithm, there's an ICML paper from this year. When we do a big scalability study to kind of see how it scales over time. If you want to watch a video about the AutoML benchmark, there was a video on YouTube. And here's some resources. Okay, so hopefully I'm pretty much on time.
Awesome. Yeah, thank you so much for being very aware of the time. I think, yeah, we really appreciate that. And thanks so much for the great overview. I think we have a ton of questions, I think, from our end. And if you're in the audience, please feel free to, post your questions in chat, and we'll try to get those across. So I guess just to kick things off, like, I'm curious about your experience with AutoML, and particular, like, I guess maybe in like the last 3 or 4 years, people in machine learning have, kind of become increasingly aware of, like, average performance not necessarily being kind of the overarching goal, right? And often, like, there, these tail cases or more like rare cases where model performance is particularly important, especially maybe in production use cases, and that you might care about, but you might not be able to, train a model that's doing perfectly on those. So do you have a sense of like how AutoML does on on these types of cases, and whether there's some sort of process by which, there's a human in the loop and there's some human feedback that goes into that AutoML process.
Yeah, I would say like in the past couple of years, there's been a little bit of an evolution of the tooling. So when I started this, I'm pretty sure everybody was really just focused on model performance and nothing else. And I see that changing a little bit. So now within the tools themselves, and this is actually something we're working on as well, is kind of forking the use cases within the tool. So rather than just AutoML trying to sort of optimize for what we assume the user's preferences are, we would like to kind of expose like different modes. So is your goal strictly model performance? Because we can give you whatever models that, these highly stacked ensembles that are very complicated, or, but not the best for production, or, more middle of the road kind of compromise between things. And then we also see like there's a big focus now on interpretability and explainability. And so like, do you want models that are explainable? So that's another aspect. We just added like a whole explainability module to H2O about 6 months ago. So yeah, I see the tools themselves kind of working into these different use cases. Maybe there's like a parameter mode or whatever where you can choose. And then you also mentioned human in the loop tools. I think that's also a newer thing. I don't personally have any experience building that type of tool, but I think I can see probably all of the AutoML tools like sort of evolving to have some aspect of that. I think some tools are just designed, I can't think of the name of there's a tool that's I'm thinking of, maybe it's from MIT, that has a like human in the loop focus, but I do think that will be more of the approach. I think possibly the scikit-learn team is thinking a little bit about that as their potential as a growth point for scikit-learn as well. So yeah, I think it's useful, and I think it's a little bit more realistic to think that a human is involved even with the fully automated tools. Yeah. It's like, I have seen use cases where a company says like, we have 200,000 users and we want to just build models for each one, and we don't want to like think about it too much. Like that is a use case. But I think if you're I would say a more common use case is like a data scientist working on like a single data set and always trying to kind of, not maybe a single data set, but some small subset of data sets for whatever their company or domain is, and they get really good at that data set. But that's where AutoML tools are lacking, is like, we're really just trying to, I think most people build a tool that works generally well, but you can do better if you have some more way to kind of insert your knowledge as the user. And that's why we see that AutoML tools are not really winning Kaggle competitions, because if you have 2 months and you have this one data set and you really just go for it on that data set and try all different data type things, you're gonna beat every AutoML tool. So yeah, I think if we want to get tools that are more useful, we should find ways to, it's just kind of a hard thing to do, to design. It's a much more complex system. So I think that's why people haven't done that first.
That seems like a great barometer, the Kaggle competition idea. Yeah.
Hey, Erin, one thing that I was wondering was, so speaking of kind of use cases that you've seen as you've, taking your tools into production with real users, what are some of the common pain points that you've noticed as users try to adopt these AutoML systems and really try to get them to work in practice? Has there been anything that's kind of been like surprising to you, problems that you didn't anticipate early on, or things like that?
Yeah, I think there's just like so many different use cases, like so many different types of data, so that if you're sort of building a tool that's meant to work on all types of data, we have like a long sort of feature list of things that we want to add. So it's more just an aspect of like, oh, a user says, oh, my data is like, has this weird like type of response variable. And, if I hand tune a model, I can get a better result than with AutoML. And I think, okay, well, we actually didn't anticipate that type of, skewness in the response or something like that. So we have to add it in. So I think like, I would say there's not like a lot of, let's say, surprises. It's more just like, I'm maybe surprised by the diversity of different types of data sets that people deal with, and that you really have to think about all of these use cases when you're building a tool. And it is kind of like an overwhelming task to think of every potential weird data thing that could happen and then make sure that your system is robust against it. And I mean, with this benchmark that we built, one of the things that we did was try to find all sorts of weird data sets or challenging data sets and make them part of the benchmark suite. So that itself has helped me to sort of find these edge cases where something just totally doesn't work, and the AutoML tool is doing, let's say, worse than if you just try to do it on your own. So yeah, it's more just nothing super unusual. It's just sort of the volume of different unique cases that everybody has, and trying to meet everybody's needs can be a challenge.
Cool, thanks, Erin.
Erin, actually, I think I have a question which is related to what you just said, so it's a good segue. I wanted to get your feedback and your experience with benchmarking in particular, because you touched upon it and you said it's like something that's very important. On one hand, I was curious about, about the benchmarking suite we were discussing about. I'm curious about what tasks are there and what are the, are they all tabular tasks, or is there something else there? But also, I'm curious about like your more general view on benchmarking and evaluating other aspects that are other than the raw performance of the model. How do you see about that? What are the aspects that you found the more interesting? What are the aspects that you think we should be focusing more as a community?
Yeah, so first of all, to answer your question, the benchmark that we have is all tabular data. So that's kind of our focus. And I think, I mean, most machine learning tools can either be in the like tabular data category or the deep learning category, or, image, text, anything, which typically means you're using deep learning. So yeah, we're very squarely in the tabular side of things. But there are tools that are more hybrid starting to come out which can handle different types of input. But yeah, for now, the benchmark is tabular data. And yeah, I mean, I don't know if you heard about, there's a new workshop at NeurIPS this coming year, all about benchmarking and benchmarking and data sets. So that's kind of like historically something that hasn't really been recognized as like a real discipline, let's say. I mean, that it has. There has been recognition for, very important data sets like ImageNet or something like that. But yeah, I think that people are starting to, at least from my perspective, I don't know if other people think this, I think people are starting to see the value a little bit more in actually rewarding people for their work on these things, like assembling a really important data set or collection of data sets or a benchmark. And I hope that we see more of that because there are some other tools, like MLPerf is another one, but that has kind of a different focus. But there's very few really, really robust big benchmarks out there. And hopefully if you can, get a NeurIPS paper out of it, then maybe people will be more motivated. But I do think that we need to measure other things, such as, anything that would be important. So some aspect of like complexity of the model, or like some, maybe that could mean complex in terms of like, if is it a fast predicting model, or is it a model that's somehow interpretable or explainable in a better way than other models? I think the hard part, like it's easy to measure model performance and prediction speed. Those are very easy things to measure. What's harder is kind of making a metric around these other aspects. So like, how explainable is it, or how interpretable is it? And I know there is some, research in this area, but it is a little bit more, it's not so cut and dry. So I think if there's more development in how to measure the tools, the tools will get more sophisticated. That's one of the harder parts about even just the benchmark that we have right now, is like, how do I measure whether, like, the way that I'm typically using the benchmark for my own development is like trying out different ideas. And if I tweak something and then I run a benchmark, like, how do I really measure if that's like significantly improved, or is it just random? I mean, we can control for things like randomness and, running it a number of times to reduce the variability and things like that. But I think we need a lot more tooling around this, and that's just going to be co-developed with the benchmarks, and hopefully people will have good ideas, because it's hard to think about this stuff.
Right. I completely agree with you, also in particular on the aspect of having multiple dimensions of evaluation. I think, like, I don't know, carbon footprint or things like that could be also, aspects that could be very important there. Thank you very much for your answer.
And just to touch on that really quickly, because one of the dimensions that I'm interested in particular, when you're, trying out different ML algorithms, is stability. And I'm wondering if you had any interesting thoughts about, because every algorithm might have a different sense of like what stability means to it. And when you go to compare them across, or just compare different algorithms across a particular data set, what do you think would be like a useful metric there?
That's a good question. Yeah, that is actually something, back to the earlier question, like when something that customers are asking about quite a lot, and there's not like a easy, quick way to, just use the whatever library in Python and it will measure. So, so yeah, I think, I mean, the most simple thing to do is like kind of look at the spread across the different folds. If you do 10-fold cross-validation, if there's like a wider spread, you're knowing that, either your data set is too small, or, just it's not a stable model. And I think there's a couple different, like, I mean, there's just assuming that you don't have like a data drift situation, which is like a whole nother aspect of like model monitoring, which is kind of its own thing. But just if assuming the data distribution does not shift too much over time, but the model is kind of different depending on which subsets you train it on, or how many times you run it, or if you if you don't set a seed and you try different seeds and it's changing so much over time. Yeah, I don't have like a good answer for you, but I think that is hopefully something that we'll see more research in, because I would like to add more tooling like that to H2O. And I think one of the sort of trends, so I'm trained as a statistician, and so we're much more thinking about like confidence intervals and things like that. And I think that in general, like the computer science community is a little bit more focused on like big data sets and like running something and like just testing it on a single test set and stuff like that. Because if you're dealing with like big data sets, it's really just a cost factor of measuring these things, I think, is kind of one aspect of it. It's very expensive to do a whole bunch of experiments and then measure the variability across a bunch of things. So I think in the statistics world, like historically, there's much more focus on smaller data sets. So we have a lot more freedom to like run things 1,000 times and measure the variability. So I think this is more like a problem of how do we figure out how to do this cheaply, and because the brute force approach of just running an experiment or a model, training a model like 1,000 times and trying to measure how it's different is just too expensive. And there are some techniques. I mean, back when I was doing my PhD, the thing that was popular was called Bag of Little Bootstraps by Michael Jordan. That was like a way to measure, sort of get confidence intervals on big data. And I did some research in my PhD as well about how to use something called an influence function or an influence curve to do very computationally cheap confidence intervals on big data sets. So there are things out there. I think that this is a time where statisticians and computer scientists can help each other out, because I think statisticians have some good tools for this, but they don't, they're not like having the right conversations with the people that actually need this. So maybe something will happen there.
Yeah, I mean, it's a hard problem when you get to the big data environment. So I'm glad to hear that you're like thinking of these kind of things. Yeah.
Hey, Erin, I wanted to highlight a question that we got from our online audience from Yuhui Shi. So they're asking, if H2O was invented today, would it have been done differently? And I guess, how would it have been done differently?
That's a good question. Yeah, I'm sure it would have. I think, it would, if I like, let's say, maybe I should just answer for myself. If I was building a new machine learning system from scratch, like, I think, hardware is such a huge piece of like performance and cost and all of this. So I think building and I don't know if this is possible, but like building a system that's not so tied to the hardware, I don't really know if that's possible, because a lot of the optimizations that you make are really specific to hardware. And so it's kind of hard to build sort of a generically good system that could somehow be plugged into different backends and have similar performance. But if that was easy to do, that's what I would do. But also, I think, yeah, I mean, I have some opinions about, like, do we need a single system to do all sorts of data types, or could we have like separate systems? Like right now, we very much have separate tools. If you have tabular data, there's a whole list of tools that work on that. If you have image data, there's that. If it's text, it's another thing. So I don't know. I mean, it might be nice to have tools that work a little bit, that play a little bit better together. I don't know that you need a single system that does every type of potential data, input that in existence. But I think if we had more sort of interoperability between the tools, that would be a focus as well. And yeah, I mean, I've learned a lot about API design over the years, and I would love to just like, sometimes just start over from scratch, like without any of the restrictions of how things were done, 8 years ago, and being able to break the API. But because of, how H2O is used in so many different like real life situations, we can't do things like that sometimes. So we have to sort of work around that. So yeah, I think I personally know a lot more about API design, and having more experience, I think that's actually a really important focus, that anyone starting from a new system from scratch, I think like that has to be one of the top things. And I think we see like kind of what happened with TensorFlow and Keras, and like systems kind of evolving on top of it. That, your system, if it doesn't have a good API, or if it's not user friendly, like people are just going to build on top of it and use you as an engine. And then you kind of lose some kind of, I don't know what the word is, you lose like the touch point with the users a little bit more. So I think I would emphasize that. And I would also emphasize like its explainability and all of that stuff, because we see people trying to patch that into like existing stuff now, and it's a little bit, janky at times.
Right.
For lack of a better word.
Yeah. I think there was another great question in the audience from Alex Ke. So he says, it seems like there's a lot of challenges in fine print potentially with using AutoML systems. So what do you think of as the ideal user or the ideal application that you envision for AutoML, and maybe something like H2O and AutoML specifically?
I would say there's definitely a couple different user profiles. So I think like one thing where I think it is quite useful, even just as it is right now, where all the AutoML tools stand, is like for people that are not machine learning people, but they are scientists doing some kind of research that's using machine learning. And you know, we don't want those people to have to learn how to tune and do all this fancy stuff with machine learning algorithms. They kind of just need like a very simple tool that they could understand just the basics of machine learning. Like here's a training set, here's the response column, here's some training, like here's some model metrics, like just some basic stuff. I think that's where I see right now where the AutoML tools are as like super useful. And I wish that like more scientists would know about them, because I see like papers all the time where they basically trying machine learning on some new novel scientific application, and they train like a default random forest, and then they're like, okay, we're done. And then and then it's like, okay, well now we know what like a default random forest could do on this particular problem, but we don't really know like how much more, like how much better we could get. I think in healthcare and medicine there's a lot of that. I see that. So that's one use case where I think we're already good. But I think that like also, at least for myself, like AutoML is really a learning tool as well. Like if you have a tool that can like easily try a whole bunch of things, and you don't have to write a whole bunch of code to do that, it's like accelerating your research process. So even if you're some kind of skilled data scientist or machine learning expert, like I think if you have a tool that you can like iterate really quickly, and maybe you're trying different like feature encodings and you want to just see which ones work, you just have a couple different versions of the training data and throw it into AutoML, and you can like see stuff. And I mean, I just learned a lot about machine learning algorithms just by looking at the leaderboard when I'm done. So like there'll be some data sets where the leaderboard's kind of weird. It's like maybe a GLM is at the top of the leaderboard, and I'm like, what's going on here? And like, why is this happening? Because it's usually not, the best algorithm. Or like, why is the stacked ensemble like slightly lower than like the top XGBoost? Like, what happened there? I mean, as a I don't know, you just learn about how different algorithms perform on lots of different data sets if you use the tool enough. And so I think it's actually a quite useful learning tool for people as well.
Awesome. Yeah, let me just get in, a couple of very quick, questions that people in the audience had. One question was about time series data and whether whether a lot of the H2O stuff has specialized solutions for time series. And the other question was around hyperopt and hyperband and whether that's relevant to some of your AutoML work.
Yeah, those are two great questions. Okay, so time series, I would say that we do have some time series capability in H2O. So H2O, the company, actually makes other products as well that are not open source. I would say half of our tools are open source, half of them are not. So we have actually a closed source AutoML tool called Driverless AI that's much more specialized for time series. But there is like a lot of people building third-party tools on top of H2O. So there's this one that just came out that's called Model Time. And that's right now it's in R only, but they're also working, I think, on a Python version. And that's like a forecasting system based on H2O AutoML. So there are tools out there that like we have not built. So I would say, yeah, if I had more resources, I would do more of that. But like we just have to prioritize like what's right in front of us. And usually, we're a company, and one of the ways we make money is like enterprise support from customers. And so I would say half of what we do is just motivated directly by what they ask. And then the other half is like whatever we think is useful. So it sort of depends a little bit on what the demand is. And so if a customer said, oh, we really want to build this particular time series thing, we would build it. So it's just a matter of sort of time and resources. And then your second question was about hyperband. And That is also something that is just a matter of having the time to add it to H2O. And it's not like it hasn't been around for a while, but it's, yeah, I think that I don't want to make any promises, but it's something that I would like to add because, yeah, I mean, random search is great and it's fine, but if you could be more efficient with it, it would be better. So it's, yeah, it's on our roadmap. I just don't know when we're going to get to it.
Okay, awesome. Well, yeah, thank you so much, Erin, for taking time out, and really enjoyed hearing the overview of H2O, and thanks for taking all our questions. Thanks to the audience for tuning in, and we're online every week. Please, join us next week. We will have Carol Jean Wu joining us, talking about recommendation systems. Also, if you haven't already, go to our website, mlsys.stanford.edu, sign up to our mailing list, subscribe to the channel, and we'll see you next time. Thanks. Bye-bye.